What if I told you that the invisible river of data that powers our world is about to burst its banks? And the very foundation of our digital existence, the silicon chip, is the dam that's about to break? Look around you. The smartphone in your hand, the smart TV on your wall, the disembodied voice of an AI that can write a poem or debug code it. It's all part of a silent, sprawling empire. An empire built on sand, quite literally. For over half a century, this empire has been ruled by a single, seemingly omnipotent sovereign, the silicon transistor. It was a simple decree that fueled its growth, a prophecy known as Moore's Law, which stated that our power would double every 2 years. And for a glorious 50 years, it did. Our devices became exponentially smaller, faster, and more godlike in their abilities. But that age is over. The prophecy has failed. Deep within the microscopic cities etched onto our chips, a crisis is unfolding. The engine of our modern world is overheating, and the relentless march of progress has finally run headfirst into the unyielding walls of physics itself. Today, we stand on the precipice of a new era, and we must ask the terrifying and exhilarating question, what comes next? For decades, the silicon transistor was our tireless workhorse, the unsung hero of the digital revolution. Its job was simple: to act as a gate, either stopping the flow of electrons to represent a 0 or letting them pass to represent a 1. The magic was in the shrinking. With every generation, engineers, like modern-day wizards, found ways to carve these gates ever smaller, packing more and more of them into the same space. This relentless miniaturization is what gave us the world we know. It took us from room-sized computers that could barely calculate a missile's trajectory to pocket-sized devices that can stream high-definition video from space. But we have finally reached the end of the line. The gates are now so small, their walls are only a few atoms thick. And at this ghostly quantum scale, the old rules no longer apply. The electrons, once our perfectly disciplined soldiers marching through silicon corridors, have begun to behave like phantoms. They are starting to tunnel right through the solid atomic walls of the closed gates, creating leaks and errors. It's as if the guards of our digital kingdom are simply vanishing from their posts, allowing chaos to seep into the system. This quantum leakage creates a far more tangible and destructive problem: heat. Every electron that moves, every calculation that is made, generates friction and a tiny puff of heat. When you have billions of transistors switching billions of times per second on a chip the size of your fingernail, that tiny puff becomes a raging inferno. Your laptop gets hot on your lap, your phone slows down to protect itself from melting. These aren't glitches. They are the death rattles of an aging technology. The heat is so intense that we can't unrun the chips any faster or pack the transistors any closer together without them literally vaporizing. Progress is suffocating in its own waste heat. We are living in the twilight of the Silicon Age, a magnificent golden sunset. But our ambition, particularly our insatiable hunger for artificial intelligence, is a rocket aimed at the stars. And it is demanding an engine far more powerful than the dying embers of silicon can provide. The age of easy scaling is over, and we are adrift, in desperate need of a new star to guide us. As the silicon engine sputters, a profound question echoes through the laboratories and research centers of the world. What comes after? What new medium can carry our dreams of ever more powerful computation? We've explored exotic materials from carbon nanotubes to graphene, and even dabbled in the mind-bending realm of quantum computing. But the most promising, and perhaps most poetic, answer may not lie in a new kind of wire, but in abandoning wires altogether. The answer may lie in light. Imagine, for a moment, the difference between a crowded city street and the open sky. The street is a world of traffic jams, collisions, friction, and delays. That is the world of the electron. It is a physical particle, a tiny ball of charge that has to shove its way through a dense lattice of atoms, creating heat and noise with every single interaction. Now, look up at the sky. That is the world of the photon, a particle of light. It flows, it glides. It moves at the ultimate speed limit of the universe, unhindered by the material world. It is a pure, frictionless medium. This is the fundamental promise of photonics, computing with light. It represents a philosophical shift as much as a technological one. It's the idea of moving from a system of brute force electrical pushing to one of effortless, silent flow. We are on a quest not just to build a faster computer, but to discover a new universe for our data, to inhabit a universe where information travels not as a frantic staccato pulse of electricity, but as a serene and continuous wave of light. This is the call of the new medium, a call to leave the crowded, overheating planet of silicon behind and set sail on an ocean of light. To understand why light holds such revolutionary potential, we need to appreciate its fundamental nature. An electron crawls, a photon teleports. That may sound like an exaggeration, but in the microscopic world of a computer chip, it's the truth. The speed of an electron in a copper wire is shockingly slow, often just a few centimeters per second, due to the constant stop-and-go traffic of atomic collisions. A photon traveling through an optical waveguide moves at nearly the speed of light itself. The difference is not a matter of degree. It's a chasm of reality. But its speed is only part of the story. Light computes without friction. Because photons have no charge, they don't interact with each other or the material they pass through in the same clumsy way electrons do. They glide past one another without generating significant heat. A photonic processor could theoretically run thousands of times faster than a silicon one while remaining cool to the touch. The very problem that is killing silicon heat is a problem that light simply doesn't have. Furthermore, light has a richness and complexity that a simple electron flow lacks. A beam of light is not just a single stream of information. It is a symphony. It has frequency, phase, and polarization. Most importantly, it has color. Through a technique called wavelength division multiplexing, a single strand of optical fiber can carry hundreds of different colors of light at once, and each color can be its own independent channel of data. Think of it this way. An electrical wire is a single-lane road. You can try to make the cars go faster, but it's still just one lane. A fiber optic waveguide is a superhighway with hundreds of lanes, each painted a different color of the rainbow, and all traffic is moving at the speed of light. Light doesn't just promise to make our old way of computing faster. It promises a new kind of computation that is vastly more spacious, dense, and parallel. With the promise of breathtaking speed, zero heat, and almost infinite bandwidth, photonics seemed like a computational utopia. We could envision a future of instant, cool, and silent processing that would make today's supercomputers look like abacuses. The dream of pure light-speed computing was intoxicating. But as scientists built the first rudimentary photonic processors, they slammed into a wall, a conceptual barrier so profound it threatened to destroy the entire dream. It was a beautiful, tragic, fatal flaw light cannot remember. A photon is a creature of pure momentum. It is born from an energy source, travels at the cosmic speed limit, and then dies when it is absorbed. It is always in motion, it never stops. And because it never stops, it cannot be stored. The moment a beam of light carries out its calculation and passes through a logic gate, the information it held, the result of that calculation, is gone. It vanishes as quickly and completely as a spoken word in an empty room. Imagine a genius who could solve the most complex mathematical problems in the blink of an eye, but in that same instant forgot both the question and the answer. That was the state of photonics. It was a mind of brilliant but fleeting thoughts, with no capacity for memory. This single devastating weakness created a paradox. To be useful, any computation needs to be stored, at least temporarily. You need to remember the result of step A to perform step B, and so, photonic chips had to be tethered to traditional electronic memory. This tether became a ball and chain that drowned the promise of light. The process was agonizingly inefficient. A calculation would be performed at the speed of light within the photonic part of the chip. Then to be stored, the result had to be converted from a photon back into a slow, clumsy electron. This photon-to-electron conversion is a slow, energy-intensive process. Later, when that piece of information was needed again, the electron had to be painstakingly converted back into a photon to re-enter the light-speed processor. This constant back-and-forth translation was the ultimate bottleneck. It was like owning a fleet of supersonic jets but forcing them to land and transfer all their cargo to horse-drawn carriages after every single mile of flight. All of the incredible speed and energy efficiency that light offered was being utterly wasted in the conversion process. The dream wasn't just stalling. It was collapsing under the weight of its own contradiction. The energy saved by using cool, efficient light was being burned up in the hot, inefficient electronic memory and the bridges between the two worlds. For computation to truly be liberated, light couldn't just be the processor. It had to be the memory too. It had to learn how to stand still. But how do you build a cage for a sunbeam? How do you teach light, the very symbol of transience, how to remember? For years, that question seemed impossible. Until now. The breakthrough came not from a single eureka moment, but from the clever combination of two existing technologies. The solution was an elegant and beautiful trap for light, a way to hold it and read its state without destroying it. Scientists, the modern-day Prometheans, had finally figured out how to give light a memory. Here is how they did it. First, they constructed microscopic racetracks for light on the chip, tiny loops called micro-ring resonators. When a beam of light containing data passes by one of these loops, a specific color, or wavelength, will peel off and begin circling indefinitely within that ring. The light is now trapped, perpetually orbiting like a tiny planet. This trapped light represents a piece of stored information. But trapping it is only half the battle. How do you change that information? How do you write a 1 or a 0? This is where the second piece of the puzzle comes in, a class of materials known as phase change materials. You've likely used this technology without knowing it. It's the same material used in the surfaces of rewritable CDs and DVDs. These materials have a fascinating property. They can be instantly switched between two different physical states. In one state, they are amorphous, like glass, and are completely transparent. In their other state, they are crystalline, like a metal, and become opaque. The scientists placed a tiny nanoscale patch of this phase change material on the micro-ring racetrack. Now they had full control. To store a 1, they would let the desired color of light enter and circulate in the ring. The material would be left in its transparent state. To store a 0, they would hit that tiny patch of material with an intense, specific pulse of light. Instantly, the material would snap into its crystalline, opaque state. The light could no longer circulate. The ring was now empty. They had written a 0. For the first time in history, computing and memory could exist in the same luminous space. Data no longer had to leave the photonic realm. Thought and memory were finally unified in a single beam of light. This breakthrough doesn't just make things faster. It fundamentally rewires the architecture of computation. For the entire history of modern computing, our machines have been built on a principle called the von Neumann architecture. This design has one crucial and deeply inefficient feature. The processor, the brain, and the memory, the storage, are physically separate. To perform any task, a piece of data must be fetched from the memory and shuttled over to the processor. The processor does its work, and then the result is shuttled back to the memory for storage. This constant, frantic back and forth is what computer scientists call the von Neumann bottleneck. To put this in human terms, imagine a brilliant chef who has to work in a kitchen where the pantry is located a block down the street. It doesn't matter how fast that chef can chop vegetables if they spend 99% of their time just running back and forth to get the ingredients. That is how your computer works today. A staggering amount of energy and time is wasted simply moving data around. The new photonic memory obliterates this bottleneck. By creating in-memory computing, the calculation happens where the data already lives. The chef is no longer running to the pantry. The pantry is built directly into the cutting board. There is no separation between thought and memory. This collapse of computing's greatest bottleneck results in a radical leap in efficiency. It's not just about saving time. It's about saving colossal amounts of energy, making computation orders of magnitude more powerful for the same energy cost. We are on the verge of machines that don't just run on light but begin to think in a way that is structurally more efficient than anything that has come before. The magic of photonic computing doesn't stop at unifying memory and processing. It unlocks a new dimension of multitasking that makes even our most advanced multi-core processors look rudimentary. This is the superpower of true parallelism. As we discussed, a single beam of light can be composed of hundreds of different colors, each operating as an independent data channel. The breakthrough of photonic memory means that each of these color channels can now have its own memory and processing capabilities built in. It's not just a multi-lane highway for data anymore. Now, every single lane on that highway is its own self-contained, intelligent vehicle, performing its own calculations simultaneously. Your current 8-core or 16-core CPU is like having a kitchen with 16 chefs. It's certainly better than one, but they still have to coordinate, share some of the same counter space, and pull from the same central pantry. This creates overhead and communication delays. A photonic processor is fundamentally different. It's like having hundreds of completely independent, fully stocked kitchens, each operating in its own dimension of color, all working at once without ever interfering with one another. This allows for a massive number of computations to happen in true parallel, not just in rapid succession. For problems that can be broken down into many small, independent tasks, the very kinds of problems at the heart of artificial intelligence, complex simulations, and big data analysis, this capability is nothing short of revolutionary. Artificial intelligence, in its current form, is a glutton. It is a mind of immense and growing potential, but it is trapped in the body of a technology that can no longer sustain it. Training a single large language model, like GPT-4, consumes a terrifying amount of energy. The data centers that house these AIs are vast, power-hungry behemoths, burning through electricity on the scale of entire cities and generating a carbon footprint that can rival the airline industry. We are trying to build a god, and we are powering it with a global bonfire. This is where the cool, silent efficiency of photonics becomes not just an improvement, but a necessity. The very calculations that form the heart of neural networks, massive matrix multiplications, are tasks that photonic processors are uniquely suited for. They can perform these operations at near light speed, in parallel across hundreds of color channels, all while generating a fraction of the heat. A photonic AI would be a mind freed from its thermal prison. It could become vastly more powerful and complex without the risk of an energy catastrophe. This could be the key that unlocks the next stage of AI development, perhaps even the path to artificial general intelligence, AGI. It is entirely possible that the primary barrier to creating a truly human-level intelligence is not just algorithmic but physical. We may have already developed the right theories, but we are trying to run them on an engine that is fundamentally too hot, too slow, and too inefficient. Photonics offers a new body for the mind of a body of pure, cool, efficient light. It could rescue AI from its unsustainable trajectory and unleash its true potential upon the world. While rescuing AI is a monumental task, the impact of light-speed computing will ripple out far beyond the world of neural networks, transforming the very foundations of science, medicine, and human discovery. We are talking about a tool that could compress months or even years of research into mere hours. Consider the field of medicine. The dream of personalized medicine is to design drugs and treatments tailored to an individual's unique genetic code. This requires simulating how millions of potential molecules will interact with a person's specific proteins, a computational task of staggering complexity. With photonic computers, we could simulate these interactions in near real time, designing a perfect cancer-fighting drug for your specific tumor in an afternoon. Think about climate science. One of our greatest challenges is accurately modeling the Earth's climate, a chaotic system with billions of variables. Photonic supercomputers could create a digital twin of our planet, a perfect simulation that could model the effects of our policies with absolute clarity, allowing us to find the true path to reversing climate change. In space exploration, probes like the James Webb Space Telescope gather more data than we can effectively process. Light-speed computing could analyze this data as it arrives, mapping the cosmos in real time and potentially unveiling the secrets of dark matter, dark energy, and the very origins of our universe. From material science, where we could design perfect new superconductors, to financial modeling that could predict market crashes with uncanny accuracy, almost no field of human endeavor will be left untouched. This isn't just an upgrade. It's a phase change for civilization itself. Yet for all its world-changing promise, the path ahead for light is not without its obstacles. We have witnessed a miracle in the laboratory, but translating that miracle into a mass-produced chip that powers your next smartphone is a journey fraught with immense engineering challenges. We have built a beautiful, working prototype of a fusion reactor. Now we have to figure out how to make it fit in your pocket and build it for a few dollars. The first major hurdle is scale. Photons, being creatures of light, operate on a wavelength that is much larger than the atomic scale of modern transistors. This means that photonic components, the waveguides, resonators, and modulators are currently giants compared to the nanoscale cities etched into silicon. Miniaturizing these components without losing their effectiveness is a monumental task. The second challenge is manufacturing. The entire global technology ecosystem, the multi-trillion-dollar infrastructure of foundries, design tools, and engineering talent is built to speak the language of electrons. Now we must learn a new art, mastering new materials and manufacturing techniques to shape the flow of light with the same precision. They are the crucibles that will forge the next generation of innovation. Startups are already sprouting up, funded by venture capitalists who see the immense potential. University labs are racing to refine the materials and shrink the designs. These shadows on the horizon do not signal the end of the dream, but the beginning of the next great engineering adventure for humanity. But it is no longer just a piece of silicon, it is a prophecy made real. It is a vessel that holds a captured star, a thought made of light. The long triumphant era of the electron, the era that gave us the modern world, is beginning to wane. A new dawn is breaking the dawn of the photon. The journey we have taken today, from the death of Moore's law to the birth of a computer that remembers with light, is more than just a story about technology. It is a profound lesson in the nature of progress itself. It teaches us that the perceived limits of today are not the fundamental laws of tomorrow. It shows us that when one path becomes a dead end, when the old way of doing things begins to overheat and break down, the solution is often not to push harder down that same failing path, but to have the courage to switch to a new medium entirely. This is a lesson we can apply to our own lives. How often do we find ourselves stuck, trying to solve a problem with the same silicon, thinking that created it? We push harder, we work longer, we try to force a solution, only to find ourselves overheating with stress and frustration. The story of light computing suggests a different way. Perhaps the answer isn't to brute force the problem with more effort, more electricity, but to step back and find a new perspective, a new approach, a new medium. To switch from the grinding effort of the electron to the effortless flow of the photon. From brute force to a moment of brilliant insight. The journey ahead for photonics is still long and uncertain, but the direction is clear. We are moving toward a future of machines that do not just run on light, but truly think in it. A future where our computational power is limited not by the heat of our machines, but only by the brightness of our imagination. Now I want to turn it over to you. What grand challenge do you think light-speed computing should tackle first? Should we focus on curing diseases, reversing climate change, or exploring the deepest reaches of the cosmos? And thinking about your own life, when have you had a breakthrough by switching your own operating system from brute force to a moment of insight? Share your thoughts in the comments below. I'd love to read your stories. Thank you for joining me on this incredible journey into the dawn of a new computational age. I hope it sparked some new ideas and left you feeling inspired about the future. Please take care of yourselves and be well. And if you enjoyed this deep dive and want to continue exploring the frontiers of science and technology with me, please do me a huge favor and hit that subscribe button to join our community of thinkers and dreamers. Until next time.